least. Fun. Okay, so rate decreases as the reaction proceeds because the reactants get used up and the concentration decreases. And we know that concentration affects rate. So we can only really figure out an instantaneous rate because the
rate is not uniform throughout the whole reaction.
exactly, because as concentration decreases, rate decreases. So rate's only going to be that right at that moment when they're both fully concentrated. Quickly, they'll be used up, concentration decreases, rate decreases. So at the end of the reaction, you're really going to be like, please, you last 3 molecules collide with each other. Right? So, and that's why when you were titrating, I'm like swirl, 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 because at the end, there's so few of the molecules left for the reactants that you have to like get them close enough to actually collide or they don't work, and then you end up going over and bright pink. Note that for the final.
What?
Like the lab final, you'll have a titration, so swirl vigorously. Although, I mean, a lot of professors in college literally grade you on the accuracy of your answer. I don't do that. You gotta learn somewhere. You can't be perfect the first 10 times you titrate something. So, Michael, how are we gonna figure out the instantaneous rate? So we're solving for R. We're gonna write.
I could write it if you think
Go ahead.
that's.
Are you thinking? Definitely be careful with your units in this module. And always. Alright, so if you typed in 1.1 times 10 to the negative third times 0.5 times 0.5 times 0.5, because that 1.5 is squared. Actually, the 1 will stay, right? Because
That's still saying there should be no molar.
there should, because there's only 2 here, and there's 3 there.
Yeah, there should be one molar.
One of them should.
And this is
And how many significant figures can you keep?
I can technically only keep 1.
Right.
So that would just be, thus that
100.
should be 100.
And I
Or
put
in
it
scientific
different.
notation, that should just have 1.
You can just literally write 100 to get one significant figure, as long as you don't put a decimal point. That's terrible, of course. Having one significant figure is terrible, but that's also not what I got. So if I type in 1.1 times 10 to the negative third times 0.5 times 0.5 times 0.5, I'm in gradients. I get a different answer. Does that matter? I don't know. Let's do it again. 1.1 times 10 to the negative third.
I got 1 times 10 to the negative 4.
Oh, it's negative 4.
My buttons are sticking. Oh, okay. Times 10 to the negative 4 would be good. Yes.
Apologize for not.
Oh, I have to continuously apologize for that. Sorry about your lab report. Sometimes I grade in the car too. Woo. Okay, so would it be 1 times 10 to the negative 4?
It would. That's what I got. But I heard
1.1.
10, so I went with that.
I think 1 times 10 to the negative 4. Is that what I actually got? Yes, 1 times 10 to the negative 4. And what's your unit? Molar per second? Yes, good. Okay, molar per second. There we go. Now we've got it. So, let's talk a little bit about rate and catalysts. So you guys have learned about thermodynamics, you've started kinetics, and how do they kind of tie together? Well, you know that there has to be an activation energy that you have to give a certain amount of energy to a reaction before it can really get going, even if it's going to be spontaneous. Right? So when you draw an energy diagram, whether it's like this or like this, okay, so quick review. Which one is exothermic, Aaron?
The second one. Wait, no, the first one.
Okay, so how can you tell?
Because it's losing energy.
Okay. So when it feels hot, it's exothermic. That is like losing energy out to its surroundings. This one's endothermic. It ends up with more energy than it started with. So it pulls energy in, feels cold. Where would I start to figure out the activation energy for these two? Where do you always start to figure out activation energy?
At the energy you start with.
Right, so the energy of the reactants is where you're going to start, and where do you end for activation energy?
The top of the hump.
Top of the hump, right there. So for an endothermic process, you start at the energy of the reactant and go up to the top of the hump. This is activation energy. Of course, enthalpy would be from there to there, or from there to there. But when we're looking at activation energy, it would be that. Now, do you all know what a catalyst is? Yeah, I'm going to run out of time.
I kind of looked pretty quickly. Isn't it like a basic shortcut to reduce how much activation energy
Right.
is there?
So if you had a catalyst, there are two kinds of catalysts. Can I remember the word? I'm absolutely... Oh, a heterogeneous and a homogeneous catalyst. So this is the other paragraph that you're going to write.
This is in the
lab help sheet. And I'm going to show you a catalyzed reaction. He talked in the book about, or maybe I'll read it this week, about hydrogen peroxide and how, according to Gibbs, it spontaneously decomposes at room temperature. It goes from peroxide to water plus oxygen. It decomposes from H2O2 to H2O plus O2. But my hydrogen peroxide still is hydrogen peroxide, even though it should be decomposing. So why is that?
The reaction's slow.
Really slow. The rate is really slow, even though energetically it's happening and possible. So that means that the activation energy is really, really high, and so it doesn't really get that much energy frequently. So the decomposition is very, very slow. So how could I reduce the activation energy? Well, catalyst can provide a pathway, right? This here is the catalyst providing a pathway to lower the activation energy so that it increases rate by getting the reaction started at a lower energy, basically. The two kinds of catalysts work this way. A heterogeneous catalyst does not participate in the reaction. But it attracts the reactant to itself. So they seem more concentrated in that area. You might want to wait a second. We'll blow something up in a second. In the area around the catalyst, they're going to be more concentrated. A homogeneous catalyst does participate in the reaction, making a multi-step process. Okay, so this does participate in the reaction. It forms some middle-of-the-road byproducts, but then the catalyst gets reformed in the end. So it never runs out. Its concentration stays constant. So it gets used but then reformed, used and then reformed. So it stays constant in concentration because it's always reformed in the end. So when I decompose this peroxide, I'm going to use yeast as a catalyst. So you're going to take a guess at what kind of catalyst yeast would be. Not participating, just drawing the reactants closer to itself, or participating and getting reformed. Can I reform little living guys? No.
It would be cool.
Right. So yeah, it's going to be a heterogeneous catalyst because I can't create life here. If we could, we'd have just
Well, I was
won the
thinking
Nobel
because it's a
Prize.
bacteria.
It's a
could.
fungus. I'm no biologist, but fungus.
What is it?
What
is that?
A catalyst was
Is it?
bacteria. Wait, no, it's a fungus.
Yeast is a
Yeast is a
fungus.
Well,
fungus.
never have a discussion about that.
Yeast is a fungus.
Because you're like,
So the normal way that you can tell the difference is a homogeneous. Homo, of course, means the same. So it is the same phase as at least one of the reactants. And in this case, since we're decomposing something, we only have one reactant. So, and the phase here is liquid. So we can see that this is a solid, that's a liquid, not the same phase. So if you're looking at a homogeneous catalyst, one factor you have to consider is if it's not the same phase as any reactants, it's not homogeneous. It has to be the same phase, same phase as thing. I need a match first. No, I'm not afraid of any of this stuff. We're making all safe stuff this time, and you guys are way back there.
are
So
you going to add this to the first paragraph?
you're going to add
Because-
this to the paragraph, just a separate paragraph. And on the lab help sheet, it just asks you basically how does a catalyst work and how can you tell what kind of catalyst this is,
The homogeneous one has the same phase as well.
as at least one of the reactants. So, I'll put the reaction up. So this is peroxide decomposing into water and oxygen gas. So how can I be sure that this is acting as a catalyst and just doing the decomposition instead of a completely separate reaction? Well, I need to make sure I'm making oxygen gas. So you can see my peroxide is not decomposing in the bottle, but something is clearly happening in the flask. So, how do I know? Is it producing oxygen? Are we producing oxygen? It's quite determined to burn, isn't it? In a high oxygen environment, of course, burning is going to be more vigorous. I should probably light something less irritating than the match. Has she rung the bell yet? Okay, not ringing the bell quite yet. So we'll just sit around burning this. But clearly we're producing oxygen. And no matter how much I keep adding peroxide to the flask, the yeast will keep decomposing it because it's a catalyst. It's not being used up in the reaction. It's never going to decrease in concentration either way, whichever kind of catalyst it is. So,
I'm gonna try to redo the
ah,
You can see the flaming.
well, once it's liquidy. I always love playing with fire. It's so awful. Now I'll have bleached out hair. Bleached skirt, bleached hair. Anyhow, you can definitely see until the liquid puts it out. It will burn happily in the oxygen. So, all right, fabulous. Finish the module over the next 2 weeks and just write the paragraphs, Kristen.
This is confusing.
Oh.